All right. Is that not the thermal chamber?
And I think
Oh, okay. Sure. Yeah, it's fine.
Hi, my name is Joshua Liberman, and today I will be presenting work on assessing misalignment tolerances for implicit electric field conjugation. So just to briefly outline the talk, I'm going to go through a brief overview of direct imaging and why we care about it. I'm then going to explain what wavefront sensing and control is. I'm going to then show my results on iEFC misalignments in simulation. I'm next going to show some results I obtained on the SCOOB testbed. And finally, I'm going to include a summary and future prospects. So just to a brief overview of direct imaging. This technique involves using a coronagraph to block out a star's light and image a planet. So here you can see beta pic B imaged over multiple epochs. And so why do we care about direct imaging? Well, it's because we can use this technique to characterize exoplanets. So other detection methods give you an indirect confirmation that a planet exists, but with direct imaging, you can actually get light from the planet itself. And with that, you can begin to recover the compositions within the planet's atmosphere. So the problem with this is that imaging planets is really difficult. You can see on this plot of contrast versus separation for planets in our solar system that Earth is all the way down here in the bottom left, and it's 10 billion times fainter than our sun. So that's the kind of contrast levels we need to achieve in order to eventually detect these Earth-like planets. So removing starlight with coronagraphy, all of you in this room are pretty familiar with this. You have in red, you have on-axis starlight. It's where it hits a focal plane mask. It's diffracted outside the mask and blocked by a Lyot stop, while off-axis light passes through the Lyot stop and hits our detector. This is the planet light. However, this is a nice ideal case. In reality, there's a lot of light that a lot of starlight ends up leaking through, and we get what are called quasi-static speckles. So in this image from the extreme AO system on Subaru, SkexAO, we see this is an image after we've inserted a coronagraph, and you see all these quasi-static speckles. And then these bright speckles here on the image these are ones that are just called good because they're applied by the DM for position measurements. But these quasi-static speckles are really what's limiting us in achieving higher contrasts. And so we need a way of getting rid of them. So this is where wavefront control comes in. As I mentioned before, so optical aberrations or imperfect optics will create these speckles, which is residual light that falls onto our final image. And luckily, using wavefront control, we can suppress these speckles. So in the animation shown at right, you can see a quasi-static speckle field before and after applying wavefront control, where we've effectively removed the speckles within a given control region. So in general, with a typical wavefront sensing and control algorithm, you would have the wavefront sensing portion would look something like this oftentimes, where you start with a model and then you apply pairwise probes to the DM. And from these pairwise images, you can update your model and recover an estimate of the electric field. The wavefront sensing and control algorithm I'll be talking about today works a little bit differently, implicit electric field conjugation, in that the sensing, that probing I showed before, and the control are combined into the same algorithm, whereas normally they're treated separately. So the idea behind iEFC is that you apply a sine wave to your DM, and then you apply your pairwise probes to recover a measurement of a wavefront measurement on the DM surface. And ultimately, you do this for a series of probes shown with these red dots in the second image. And ultimately, with this series of modes and probes, you construct a Jacobian. Using this, by inverting this Jacobian and using linear least squares, you can implicitly minimize the electric field within a given region of an image. However, oftentimes when we're using this wavefront control algorithm, we assume a perfectly aligned system, but the reality is that optical systems are often subject to misalignments or drifts. So the question we're examining is, how is iEFC's performance impacted by these optical system misalignments, and how well does it do in the presence of misalignments? So to address this, I developed an end-to-end optical simulation in HCI loosely based off of the current MagAO-X layout. So in one of the simulations, I use a vortex coronagraph with a circular aperture and a 1K DM. And then in the other simulation, I use the Magellan pupil as well as our instrument's pre-apodizing mask and a perfect coronagraph. And MagAO-X is our extreme AO system located on the Magellan telescope. So these are just some figures from the simulations. So here on the left, we have a simulated stellar PSF after correction with iEFC. And then on the right is our pre-apodizing bump mask, which is basically a mask we apply over our pupil to hide a defective actuator. So in the test cases for this simulation, what I do is I compute a Jacobian for iEFC, and then in the Jacobian, the response matrix I take is for a perfectly aligned system. And then after that, I gradually misalign a given optic and examine iEFC's response to this misalignment. So in the first case, I'm misaligning the focal plane mask with respect to the detector. I'm then examining the effects of DM misregistration, where the deformable mirror is slightly misaligned with respect to the pupil. In the third case, I'm examining effects of a slightly off-axis or offset Leo stop. And finally, in the last case, I examine how iEFC performs when this pre-apodizing mask on MagAO-X is slightly misaligned. So just as a quick example of what I mean by these misalignments, for a focal plane mask, when it's misaligned, basically this is showing the focal plane mask or a PSF as for various off-axis positions with respect to a focal plane mask. And the idea basically is that you're going to have this is a bit dramatic, but in general, when you're misaligning the PSF, you're going to end up with more of these quasi-static speckles in your final image. And that becomes difficult to remove. So as far as the end-to-end simulation results, I first examined focal plane misalignments on our detector. And what we see in simulation is that iEFC is able to converge for these focal plane mask offsets within 1 lambda over d. So that's encouraging because on MagAO-X, we are able to align our system within 1 lambda over d. We're able to align the coronagraph to that accuracy. I then examined the pupil misalignments on the DM, so where I'm misregistering the DM. And in this case, we observed that the pupil must be aligned to within one DM actuator before the solution begins diverging. So I next examine Lyot stop alignment sensitivity, and somewhat unsurprisingly, the Lyot stop is more resilient in simulations to, or iEFC is more resilient to these misalignments at the Lyot stop, because ultimately what's most important with the coronagraph system is that your focal plane mask is perfectly aligned, because if that's slightly off axis, then you're going to end up with a lot more light leaking through your system. And finally, we looked at the case of the bump mask. And this, the results are pretty dramatic, where if you misalign the bump mask by anything more than about 1% of the pupil diameter, then the solution immediately diverges. And this is also an issue at present with how we run iEFC on MagAO-X, because we're noticing that the bump mask that we're using is the bump mask for our internal source is slightly different from the one we use on Sky. And so that's kind of affecting our calibrations and ultimately the accuracy of our iEFC solution and the contrast we can reach. So I then performed experiments with the SCOOB testbed, the space coronagraph optical bench, and it looks a little smaller as of late because it's currently in a temporary location on the 5th floor, although it's going to be moved back to vacuum shortly. So I was running my experiments from this temporary location. In this image, the room looks a bit cleaner than when I was in there, but we've made solid progress in cleaning the room and establishing it as a clean room. So the procedure for my experiments. So first of all, I was kind of limited in the test cases I could do with the coronagraph or with the testbed, in part because unlike simulation land, there are other people trying to use the high contrast testbed, so I'm somewhat time limited, but also obtaining pupil plane images on the testbed isn't super straightforward. So ultimately the test case that I evaluated was for misalignments of the focal plane mask. And so I followed this procedure shown here, where I start by aligning the PSF on the vortex, and then I apply a waffle pattern on the DM to induce speckles. And these are these 4 bright spots shown here. And I measure the centroids of these speckles to get an initial starting position. I take my Jacobian, I run iEFC, and then I shift the PSF along X, and I again measure the speckle centroids to see how much the PSF has shifted. And through this process, I can quantify actually how much I'm shifting the PSF with respect to the focal plane mask in lambda over D. And so I repeat this over a few different shifts of the focal plane mask, but briefly, I just want to get into, I encountered a lot of challenges with real life dark hole digging because it was my first time actually doing this on a test bed as opposed to in very nicely controlled simulation land. So one thing to note for digging dark holes is you need sufficient signal in the dark hole, particularly as your dark hole gets to deeper contrasts. So this can make iEFC time consuming, particularly for me when I was just trying to figure things out initially, because I have to keep adjusting the exposure time and making sure that I have enough signal within this dark hole to actually continue recovering the wavefronts and correcting for them. And so this particular run, I struggled a bit more, and it took me 170 iterations to reach 10 to the minus 8, which is less than ideal. However, dark hole digging can also be fun. This image is adapted from a nice figure by Jay Cuny, and this is one of the dark holes we dug on iEFC, and then you can also add a nice little face to it. So ultimately the results from my experiments, so as I shift the PSF off axis, we see that at around 0.8 lambda over d, the contrast or the solution diverges. And this is similar to what we see in our simulations, where we get this divergence at around above 1 lambda over d. And this makes sense that the simulations would be less sensitive because we have more wavefront errors within our actual test bed than within the simulation results. So to briefly summarize the work, developing this kind of iEFC tolerancing budget allows for relaxed telescope stability requirements, which is particularly important for future space-based missions such as the Habitable Worlds Observatory. And we noticed in the case of MagAO-X that our solution is highly sensitive to misalignments of our pre-apodizer or bump mask. And this isn't super surprising to us, as this mask hides a defective actuator. So when you misalign it, you now have a defective actuator that the iEFC solution doesn't know about, as it's trying to command a DM to basically dig this dark hole. We found for the simulations, as I mentioned before, we obtain similar results where in lab, our solution begins to diverge at around 0.8 lambda over d, whereas for our focal plane mask, we see this a divergence at slightly above 1 lambda over d. And then as far as next steps, I'm going to run more simulations for iEFC, but this time with the Hadamard mode basis. So briefly in that diagram of iEFC, I was using a basis of Fourier modes or sine waves applied to the DM, but this mode basis of Hadamard modes is the one that's actually used on the Scoop testbed, typically for iEFC, because it's shown better performance. So by running these simulations, this will help inform future experiments on the high contrast testbed. I will also perform these simulations and experiments in broadband, because here I was using monochromatic light. And additionally, I plan on repeating these with the internal source on MagAO-X, yet another lab measurement for our tolerancing with iEFC. So, yeah. Thank you.
In the slide you showed from the lab,
Yeah.
there's one part, yeah, like on the left side there. What's that sudden drop in contrast?
Yeah, I forgot to mention that. So the sudden drop is from, that's the technique we use when digging dark holes in the lab, where you define an initial control region, and then to achieve higher contrast after a few iterations, I then shrink the control region. So that sudden drop is from me beginning to use a smaller control region. And so that has significant effects on improving contrast within the lab. Yeah.
About the scale of intensity, is a different normalization, or why are they different? Or it's just the intensity of the source which is different, what you predict?
So the normalized intensity, as I'm defining it here, is the intensity of our is the intensity of our image after the coronagraph divided by the on-axis, the intensity from our on-axis source without a coronagraph. And I want to say, I mean, the differences you might be seeing mainly just come from in the simulations, actually, I might have misspoken here. We don't reach quite as deep contrasts as we do on the testbed. And that's because I'm simulating 75 nanometers of wavefront error. But on the testbed, I want to say, or at least in testbeds in general, you get around 10, maybe. Yeah. So this is why for our lab results, we actually achieve general deeper contrast than in the simulations. So another thing I will want to do as far as what I simulate is rerun these simulations, but for the same amount of wavefront error that we're seeing on the testbed. So I think that would be a bit more informative as far as like an apples to apples comparison between the simulation and lab results. Yeah.
What pairwise probes are you using?
So these are basically sum, sine, and cosine probes. Yeah.
Did you, when you were using this, did you see any like print through of those probes? Because you were doing like, were you doing 3 of those for?
I was doing 2 of those.
2.
Yeah.
And they were just like shifted with respect to each other, or?
Yeah.
Okay, because we've seen sometimes you get in your DM command, you'll like just start accumulating like extra amplitude at the areas where your probes have like the largest demand. So like if you have a probe that's here and here on your DM, as you dig your dark hole, you start to accumulate like a weird term there.
Oh, interesting.
And I don't know if Keon has seen that both in simulation and in the lab. I've seen it in the lab. I started using probes that were just more evenly distributed across the DM.
Yeah, I guess
specifically
that,
to avoid that.
I guess that's how you would
I didn't
mitigate
see
it.
it in the commands that you were showing, at least the ones at the beginning.
Yeah, I wasn't noticing that really, but I also wasn't
The regularization.
explicitly
Yeah.
looking out for it.
Do you know what regularization you're using here?
I want to say I was kind of going between 2.5 and 3.5, but I'm forgetting the power exactly. Times 10 to the minus 2 or something like that.
Okay, interesting.
Yeah.
And this and quasi speckles are due to the optics.
Yeah, so these are caused by light leaking through the optics, and then the challenge with these speckles in particular is that they slowly evolve over time, and so that makes them really difficult to remove in post-processing. So really you need these active wavefront sensing and control loops to remove these particular speckles. Yep.
But they are generated by dust, because if they are optics issues, they should be static, or if they are a combination with atmospheric or telescope speckles. Why is the reason why they evolve, why they change?
Yeah, I mean, probably thermal effects, right? So you're
Thermal
making
effects.
this slowly shifting on each optic.
Okay.
So then so then I think they would slowly evolve. So yeah, I think if you could completely stabilize your system, then they wouldn't. Provided that your DM is stable enough like that.
So you can control is it a problem of the velocity, why that they evolved? Is it a problem for your process? Because otherwise you can use some methods in order to stabilize it even more, control the temperature.
Yeah, I mean, we for these tests we were controlling temperatures, so they probably were slowly evolving. which probably, yeah, is another, like, it's basically giving you another misalignment source, just
Yeah,
you're not
that's
controlling for. But it should be smaller than the misalignment you're inducing.
Yeah.
But yeah, I think it does limit you because it's evolving while you take your response matrix, your Jacobian, and then it's also evolving as you dig. So yeah, it should limit you at some level, but we haven't tried to really stabilize. I mean, when we're running this in our, so when it's not upstairs, it's downstairs in the vacuum chamber. And even just running it in there with the door closed, you get much more stable, and we gain almost like an order of magnitude contrast just by doing that.
When is it moving back to the vacuum out of curiosity?
Like the next few weeks.
Or if anyone online has questions?
This is Romeo.
Oh, okay.
Oh, yeah, that's a question. That,